3.1. All right, so 3.4 concavity second derivative test. We're probably going to get through this in 2 days, today and tomorrow. The first thing I do want to announce is that I have to be out Thursday for a couple more doctor's appointments. And so we're going to move the memorization test from Wednesday to Thursday, if that's okay. Just because a sub can hand you a piece of paper and it's easier to cheat when I'm not here monitoring you, right? That's really the main reason. Yeah. Yeah. So then you'll turn and you're not going to lose any instruction. I think that's better than me playing a video, right, when I'm not here. So yeah, you'll take the test. So we'll move it to Thursday. So the memorization test, which will be your first test, it's going to be Thursday. And it was asked, what section should we study? And I would say a 1.1 through 3.4. Right. Yeah. So if you get a hold of one of the tests that Ms. Skurhut gave to the AB class, it might resemble that, but I might add some stuff. I might take some stuff off. But anything that I'm expecting you to know, especially if it's been in a box, anything from pre-cal you need to know, like unit circle stuff. Yeah, so you might want to go back and look at that. I might just put like memorization, like cosecant of 5/5, and you just write -2 square root of 3/3, and you move on to the next one. Okay, it'll be on paper, so all you'll have is your paper and your pencil. Okay, so anyway, that'll be Thursday. All right, so we just finished the first derivative, and remember, the first derivative tells us what about a function? Anybody? What about a function? The slope. It tells us the slope of the function at any given point, right? And so if we know the first derivative is positive, we know that function has a positive slope there, which translates then to that function is doing what? If the slope is positive, increasing, right? And then if a function has a negative derivative, at that point, the slopes are negative and the function is decreasing, right? So that tells us part of the story. So we really have two functions now. We have the y value function that tells us where the function is, right? At this x value, it's here, at this y value. Then we have the first derivative that tells us if that value, wherever it's at, is going up or going down. Now we're moving on to the next little piece of information that gives us insight, and it's the second derivative. Okay, turns out that the second derivative of a function gives us the concavity. Okay, so there it is in Cambrian math. Concavity is synonymous with the curvature. All right, it's the curvature of a graph. So if we look at this example 1 right here, let's say we have some function f of x, and let's say that f prime is greater than 0 on some interval. What does that tell us about that function? Not just that the slopes are positive, but that it's what? It's increasing. Okay, so I have an increasing function on some interval. I want to tell you or draw and tell you that there are actually different ways a function can increase, right? So let's just come out of the origin just because it's easy. So I drew these little first quadrants. So the first way that a function can increase is like this. Okay, so this function will say f is increasing. The y values are going up. But how are they increasing? We're going to say at a what rate? At a constant rate. At a constant rate. At a constant rate. How else can we go up? Well, start at the origin and draw like part of a parabola. Now it's curving. Whenever you have a graph that curves, that's more interesting. That's where calculus is kind of needed. Here, f is increasing. No, well, exponentially would be kind of a layperson's term. If something increases exponentially, it might actually be quadratic growth. You'd have to quantify it. So in this class, when we say something is growing exponentially, it's not just an adverb, right? It's actually a term. But I want to say it's increasing at a what rate? Increasing at an increasing rate. All right. Now, the other way is coming out of the origin. It can increase at a decreasing rate. F is increasing, sorry, at a decreasing rate. So if our goal is to use the equation of the function's information to obtain information about the graph, the first derivative is good. It tells us if it's going up or down. The y values are certainly good. They tell us where they are. But the second derivative is going to tell us, bless you, the curvature. Okay. Now let's see why it's the second derivative of function. Why is it so obvious that the second derivative should be the thing that tells us the curvature? Well, you have to remember first and foremost that f prime tells us how f, which are the y values, change. Right? Anytime you take the derivative of a function, it tells you how they change. Therefore, f double prime, which is the derivative of f prime, yes, tells us how f prime, which are the slopes, change. Right? So f double prime certainly is the second derivative of f, and you'll see that it does give you the curvature of f, but it also tells us how f prime is changing. So let's take a look at it. If f prime, as Jackson said, are the slopes, come over here. How are the slopes changing? As we go up in the first case, are the slopes changing at all? No. So we're going to say slopes of f are not changing. So if you had to quantify no change, what value would you give it? Zero. Very good. So in this case, f double prime equals 0. Okay. No curvature. 0 curvature. 0 concavity. I would agree, right? That line is straight. Is it curving at all? No. 0 curvature. The slopes are not increasing. The y values are increasing, but the slopes are not. Now over here, let's look at this one. If you draw a tangent line here, that might be like, let's just call that 1/2, hypothetically. And then right here, we have another tangent line. It's a little bit steeper. It's like 1. And then here we have a tangent line. It's steeper yet. It might be like 3. What's happening to the slopes? They're getting bigger. Yeah. Here, now the slopes of f are increasing. And so the derivative of the first derivative should be what sign? Positive. The derivative of the slopes should be positive. Well, that's the second derivative. The second derivative then is greater than 0 on that interval. All right. And when the second derivative is greater than 0, we say the graph is concave up, like a cup, which I abbreviate CC up. Don't do it on the AP exam, but it's easier to put CC, right? Hi, welcome to CCs, right? Now, in the second one, let's draw this. It's going up, but here we have a slope that might be steep, like a 3. Here we have a slope that might be less steep, like a 1. And over here we have a slope that could be like 1/2. So even though the y values are increasing, the first derivative is positive. Here, the slopes are decreasing. And when I say slopes, I mean the slopes of f. It's not really good to just say slopes, because I could say what? The slopes of Colorado, right? Slopes of f are decreasing. And so what that means is f second derivative is negative. Remember, you always want to justify, as I said, using a sign or how a sign changes. So the slopes of f are decreasing means f prime's derivative, which is the second derivative, is negative. And we say that that is concave down like a frown, right? Concave down like a frown. CC down. CC up, CC down. All right, so you can read all that, but that's what we just did, okay? So here's the deal. What we're going to do is we're going to look on intervals, and now we're going to look at not just what are the function values or the y values, not just what are the derivative values, but what are the second derivative values. And sometimes the equation tells us information about the graph, and sometimes you can look at the graph and determine first and second derivative information, right? Yeah. That's how I was all day on Friday with that little drum set. I was just like running around knocking stuff over just to get like kaboom, right? Yeah. Okay, so Here's an interesting way to remember it, right? These are memes that I made up on imageflip.com, I think, back in the day. So yeah. So when the second derivative is greater than 0, the graph is concave up like a cup. So just imagine a guy, he's happy, like Hank right there, smiling. If I zoomed in on Hank, I would see plus signs in his eyes, right? Plus signs means positive. I'm positive, I'm happy, and I'm smiling, right? Not in golf, right? Minus signs are good. Yeah, yeah. Golf is like one of the few sports that the better you are at golf, the less you play, right? Right. Fewer strokes. And then this is Joe Biden, right? It's Jeff Dunham's dummy, right? The old man, but it looks a lot like Joe Biden. It looks like Joe Biden. So anyway, Walter, I think is his name. Yeah. He's frowning, right? And if you look real carefully at his eyes, they're just little slits, right? So when the second derivative is negative, right? Concave down like a frown. Okay. Now, when we say like a cup, you could also say like a smile, but it doesn't rhyme. Okay. But it could be like decreasing concave up or increasing concave up. So any part of a smile, it could be increasing concave down or decreasing concave down. And then if you get 0 for the second derivative on an interval, then there's 0 concavity, right? Curve depravity, 0. So there's zeros in his eyes, and he has that angst look on his face, which is straight line. Okay. All right. So here's what we're going to do. We're going to take this little, this is example 2. We're going to take this circle that I partitioned into 4 different arcs, and we're going to kind of go backwards. Instead of using F prime and F double prime information to sketch it, we're going to look at the graph and infer what the sign of the first and second derivative are. Okay. So on this section here, let's just write what it is. This function is increasing on this interval, and it's CC what? Down. Good. Any part of a frown is CC down. So what is the sign of the first derivative? We're going to put inequalities in here. First derivative is positive, and the second derivative is negative. Good. There you go. See what we're doing? Yeah. Let's move left to right here. On the next interval, the function is decreasing, and it's still part of a frown, so it's CC down, right? Now, because it's decreasing, the first derivative on that interval should be negative. And because it's concave down, the second derivative should be also negative. Not necessarily. Bottom left, this function is decreasing. Concave what? Up. This is part of a smile. So the first derivative is negative, and the second derivative is positive. And then on this interval, it's increasing, still part of a smile, so it's CC up like a cup. It holds water. So here's positive, positive, right? Now, when I drew the examples up above in those 3 sections, I drew the one that makes a lot of sense. But there's one that kind of gets people a little bit confused, and it's this one here, all right? So if I look at this, I can see clearly that the y values are going down, right? So I know the first derivative is negative, but look at the slopes. Look at the slopes. I have a slope here. I have a slope here. I have a slope here. Okay. Some people might look at that and say the slopes are increasing, right? I don't know. Would anyone look at that and say the slopes are increasing? Like if I were skiing down, the one on the left versus the one in the middle versus the one on the right, it's getting steeper, isn't it? But in this class, are steepness and slope the same? No. Steepness is a scalar quantity. It has no sign. Slope in this class is a vector, right? So if you put numbers to it, this could be like m equals, let's say, -1. This could be right here, m equals -2, m for slope. This could be like, negative, this looks dangerous, -1,000, right? What's happening to those numbers? Are those numbers getting bigger or smaller? Those numbers are getting smaller, right? So even though the steepness is increasing, the slope is increasing, okay? All right, and then where else? This one is concave up, coming concave down. Yeah, okay. So just be aware of that. Let's write that as over here. Slope in this class is a vector. Steepness is a scalar. You could talk about steepness in any direction, but slope sign matters. All right. Just want you to know that. Okay. So now we have a definition, and you know the name, right? We've seen it before. An inflection value, we're going to say at x equals p, is basically a place where the place in the domain. It has to be in the domain, right? We're not going to talk about an inflection point if there is no point, right? If there's no point, what's the point, right? There is no point. What is the point? I don't know. If it's not there, why talk about it? So it has to be in the domain, but it's where the graph changes curvature. It's where the concavity changes. Okay. And I wrote in there, it can change in any fashion, concave up to down or concave down to up, either one. We don't make the distinction with inflection values like we do with local max and local mins, right? For a local max, we're looking for the first derivative to change from positive to negative. For a local min, first derivative changes from negative to positive. But if we have a graph that goes from concave up to concave down versus concave down to concave up. Let me get rid of this right here. Concave down to concave up. We don't make the distinction. Like there's not like a local max, local min. We just call them both inflection points. Okay. We call them both inflection points. Now, just like with local max and mins, though, we'll just call them local extrema. What we're doing to find inflection values and intervals of concavity is the exact same thing we did in the previous section when we were looking for critical values and local extrema. Okay. So what did we do? We wanted to find out where these possible values could exist, right? So let's think about it. If the function goes from concave down to concave up, that means the second derivative, oops, I put two F's instead of two primes. It goes from positive on one side to negative on the other. And so going from a positive to a negative number through a continuum, we're going to have to pass through what? Zero. So those are going to be your candidates for inflection values or inflection points, okay? Where the second derivative is zero. Same thing over here. This one goes from, we'll just say f double prime is positive, f double prime is negative. So at this point, the second derivative is zero, okay? Now, where else could critical values occur? Not just where f prime was zero, but where f prime was also undefined, right? That goes for concavity as well, because you can have something do this. Just think of like a shark in the water, right? And it's a red tip shark, a very rare one, okay? What's happening here? You've got, in fact, the waves themselves could be cuspy, right? This is CC up like a cup, and this is CC down like a frown. So the second derivative is positive on this side and negative on this side. Did the curvature change? Yeah, it did. Is this shark tip in the domain? I don't want to touch it, but it's there. Yeah, it's in the domain. So by definition, is that an inflection value? Did the curve? Yeah. Now, what would be the value of the derivative there? The second derivative? Undefined. Good. Because what's the value of the first derivative there? Undefined. Yeah, the function's defined, but because there's a cusp, the slopes aren't the same, the first derivative is undefined. And if the first derivative is undefined, so will the second. Okay. Now, is every critical value a local extrema location? Did every critical value end up being a local max or local min? No. Same thing here. We're going to be looking for values where the second derivative is zero or undefined, as long as you're in the domain, but not every one of those values is going to end up being an inflection point. Case in point, what if we just have one of those waves, a green wave, right? Don't swim in here. It's full of algae, right? CC up on this side, CC up on this side. What's the value of the second derivative there? DNE, right? There's a cusp. So the first derivative is undefined, so is the second. Did the curvature change? No. So this one for the first time is not an inflection value. Okay. So it's really the exact same thing that we did in the previous section. We're just doing it like one rung higher on the derivative ladder. We're going to be looking for critical values essentially of f prime. And we're going to set up a number line chart with f double prime and test values. And it's going to give us information. But instead of increasing, decreasing, it's going to give us concave up, concave down info. Okay. So that's nice. We can tap into the same skill set. All right. So here's what we could say. We could say, like, you remember doing analogies? We could say, well, let's you could look at these examples here. Now let's look at this one here. I drew them. Look at this one here on the far right. Is x equals p in this case in the domain of the function, the way I have it drawn? No. We have a vertical asymptote at x equals p. So it's not in the domain. Can it be then? Does it have a chance at being an inflection point? No. If it's not in the domain, it can't be an inflection point, can't be a local extrema. But can the curvature change there? Yeah, it doesn't have to, but in this case, it's concave down on the left and concave up on the right. Did the curvature change at the vertical asymptote? Yes. Are we going to call it an inflection point? No. So if our discontinuities are there, just like on the first derivative number line chart, we're going to put them into the chart. They're important, but we're going to put them in as dotted lines. Because if we're asked to determine an interval where a graph is concave up or down, we would need to step over it. Okay. So now that we have that, let's learn this definition. And this is my term. This is the first year I'm using it in print. There needs to be a term for this, and there hasn't. There is none. We have critical values, right? Critical values of f are values where f prime is in the domain, or f is in the domain, but f prime is undefined or DNE, and they're the possible locations of the local extrema. I'm calling this now a pivotal value, and hopefully it'll sweep the nation. In the past, I just called them possible inflection values. Yeah. Do you have the old notes? Do you download them from the internet? Yeah, I changed them. The ones that are in Canvas are the new ones. Possible inflection value. I used to call them PIVs for short. But then I was thinking critical value. Critical means important, but now it's a term. You know what other kind of word means important? Pivotal. A pivotal value is important. And oh, by the way, it has the first three letters, possible inflection value. It is the perfect word. And there is no word for it. So now I'm sweep the nation. So I'm going to define a pivotal value, PV, instead of CV for critical value. It's an X value in the domain of the function where, believe it or not, either the second derivative is 0 or the second derivative is undefined. And to help you realize it, these are essentially the critical values of f prime. Okay, so we could say CVs are to f prime as PVs are to f double prime. Y'all know this notation with the colon and the double colon? Have y'all seen that? Yeah. It's the old way to write analogies. And they used to be on the SAT like that. Critical values are to f prime as pivotal values are to f double prime. Okay. Yeah. All right. Braille, they call it. Yeah. Blind dots. Nice. All right. So here's two theorems. Okay. Theorems are mathematical laws. We have to obey them. The graph of a function can change its concavity either at a pivotal value or at a discontinuity. Boy, that's just like the previous function that said a graph can only change from increasing to decreasing or vice versa at a critical value or a discontinuity. And an inflection value can only occur at a pivotal value, just like a local extrema can only occur at a critical value. But not every pivotal value is an inflection value, right? As we just saw with the namaste. Well, yeah, we did namaste, concave up on both sides. Just like not every critical value is a local max or min. There's a lot of parallels here, all right? So here's what we're going to do. We're going to test for intervals of concavity. And if you want to read this, you can, but it's essentially the same thing we did with f prime. We're just doing it with f double prime. Got it? Okay. Now, it's nice to start with a little graph because it kind of gets us, it's visual. We could see things. The graph of the function f is defined everywhere on the interval from a to k. All right. Go ahead and list the pivotal values. Well, if we have a graph, we could just look at it. A pivotal value is where the second derivative is 0 or undefined. And they're marked conveniently at the important values. They may be pivotal, they may not be. Let's look at A. We'll go through each of these. Is A pivotal value? Well, it has to pass two things. Is it in the domain? And is the second derivative 0 or undefined there? It is in the domain. Is the second derivative defined at an endpoint? No. So will a second derivative be? No. So it is a pivotal value. It's pivotal. Now, it's not going to have a shot at being an inflection point, just like it doesn't have a shot at being local max or min. I don't know what's happening on the other side. So you can be a pivotal value, but you don't get to go, whatever. B, is that a pivotal value? Concave down to the left, so the second derivative is negative. Concave up to the right, so that the derivative is positive. Well, here's the thing. We're going to go on what you said. That is a weird spot to put it. Is it further to the right or is it further to the left? You can't visualize the exact location of an inflection value from a graph. You can't. You can visualize the location of the local max and local mins, but inflection values, all you can do is narrow it down to a vicinity. And that's why the math is so important, as you'll see here. So yes, B is a pivotal value. What about C? Good. Concave up like a cup, concave down on the right, second derivative changes signs. Yeah, how about D? Yes. How about E? It's not a pivotal value? Pivotal values are, remember, PIV, possible inflection values. That's why I put pivotal, possible. It is a possible. What about H though? Ah, is it in the domain? Yes. Yes. I see the dot. Is the derivative defined there? No. So will the second? No. So H is a pivotal value. What about K? Yes. They're all pivotal values. Surprise. They're all pivotal values. Now remember, just like critical values are possible relative extrema, pivotal values are possible inflection values. PIV. It's in the game. It's in the name, actually. Now, at each PV, determine if it's an inflection value, yes or no. The values are the X's, the points are the X and Y's, right? So I'll use those sometimes interchangeably. An inflection value and an inflection point. That just contains the Y value. Now, let's just go through and list them, and we can justify without writing it down because it takes a while. Is A going to actually be an inflection value? We're looking for a change in concavity. No. Sorry, A. What about B? Yes, concave down on the left, concave up on the right. So if we were going to justify it, remember, you always want to justify by talking about a sign or a sign change. You would say, yes, B is an inflection value since F double prime changes from positive. Well, you always want to talk about a sign or a sign change, remember, right? So instead of saying F changes from concave up to concave down, which is not incorrect, we want to say since F prime changes from negative to positive, not in France, but at X equals B. The justification for concavity or an inflection point is almost identical to the justification for local extrema. Okay, let's write that so we can have a template. Okay, B, X equals B, comma, because F double prime changes from. Now, here's where you don't want to say F double prime changes from concave down to concave up. That's F information. F double prime changes from negative to positive, where? At X equals B. It's identical to the first derivative test justification for extrema, local extrema. We're just doing it for inflection points. Okay? Always talk about a sign or how a sign changes when you're justifying. It'll get you through every door. Sometimes the talking about local max, it goes from increasing to decreasing. Yeah, it's true, but I need something stronger. Concave down to concave up. Yeah, I can see that, but what's the essence of it? This is the essence of it. You're telling someone you know that you're looking at the core of the DNA of the graph, the nitty gritty. Right. Okay. So I'm not going to write the justification for the rest of them, but we'll just write down what the other values are. What about C? You can look at concave up, concave down. That's easy to visualize. That's why we're doing it. But when you justify, you talk about the second derivative. Okay. Part C, it goes concave up on the left, concave down on the right. Is that a change in curvature? Yeah, C is. What about D? Yes. Concave down to concave up? Yeah, D, welcome. How about E? No. Concave up like a cup on the left, concave. Oh, it just goes up again. Yeah, any part of a smile is concave up. Any part of a smile is concave up. Yeah, look at E. Yeah, smiling, smiling. So sorry, E, you're not one. How about H? There's a hole there, but look at the curvature. It's concave up on the left and concave down on the right. It is a possible inflection value. Did the sign of the second derivative change? Yes. So H is. Is H also the location of a local extrema? It sure is. Yeah, it's a local max. Okay. So remember, discontinuities can be local extrema. Discontinuities can be inflection values. So yeah. And then what about K? Nah. So of the 1, 2, 3, 4, 5, 6, 7 PVs, only 3 of them ended up being IVs, inflection values. 4? B. Oh, I forgot to put B in there. Oh, yeah, we justified. So let's get the whole list right here. There we go, 4. So 7 PVs and then 4 IVs. Okay. You understand the difference? Okay. So it says list the open intervals where the graph is concave up, down, or constant. Let's just do one of them. I should change it to, what do you want to do? Concave up or down? Okay, let's do all of them. Okay. So in a complete sentence, F is CC up, and then we can abbreviate that all the way through the day of the AP exam where we write out concave, right? F is CC up on, and these are open intervals. So it'd be from B to C. No, see, that's where you want to be careful. F double prime would be positive on these intervals, which means F is concave up. And it says to list the open intervals on where F is concave up. Now, if it asked you to justify, you would say F is concave up on the interval from B to C because F double prime is positive on this interval. Does that make sense? F double prime, we look at the sign, F tells us the concavity. Okay, so from B to C, concave up like a cup. How about from D to E? So union D to E. And then, is that it? We could do E to H. Very good. And that's it, right? Oh, good. Can we just do D to H? Good question. Can we step over this piece? Well, remember, if you're saying from D to H, you're saying that the curvature exists. Does the curvature exist at E? No. If the second derivative doesn't exist, then the curvature doesn't exist. So Mason, what is the answer to your question? Can you go straight through? No, you got to step over it. Okay. And then we'll say and concave down, CC down, like a frown. I'll use beefy brown. Concave down, beefy brown on the interval, beefy. A to B. Union concave down from C to D, beefy. Put an extra packet of ramen beef flavor in there. Union H to K. I didn't get that one wrong. All right. And is it ever, I like the seafood one. It tastes authentic. Yeah, this tastes like real shrimp. How do they get the shrimp to powderize like that? All right. Is it constant on any interval? Constant would be straight line. Good. No, there's no straight line. Okay. And it could be a straight line like this. It could be a straight line like that. What about a horizontal line? Could it be that too? Yeah, it could. Because look, this could be like y equals mx plus b. And what would the second derivative be? Well, what would the first derivative be? By the power rule, it'd be m, which is a constant. What would the second derivative be? 0. Yeah. So the math works out. Or if we do this one, this would be like y equals k. It's just a horizontal line. What's the derivative of a constant? 0. What would the second derivative be then? 0. Yeah. So any part of a straight line, imagine the guy like with the straight line, like a hockey puck in his mouth that I drew up there, right? Where was he? He's filled with angst, right? So any angst-ridden smile has zero curvature, zero concavity. All right. All right. So important ideas to reiterate. I've been reiterating all along. If you want to read it, feel free. We're jumping into example 4. This is where it gets good. All right. It's been good so far. How are we doing on time? I'm just this time thing. Okay, cool. So for each of the following functions, we're going to find, first of all, the PVs, pivotal values, and then the inflection values with the justification. And then we're going to list the open intervals of concavity. Now, that's a lot for one particular problem. You might be asked for any one of those things. So if we prepare for all 3 of them, we can answer it appropriately. Okay. So what do I need to do first? Even before I take the derivative. Yes, find the domain. Always first. You're introducing yourself to the problem. What's up, y equals 3 plus sine of x? I've met a couple of y's before in my life, but nothing quite like you. On the interval from 0 to 2 pi. 0 to 2 pi. Are there any discontinuities for this function? No. Sine and cosine are continuous everywhere. Had that had a secant in it or any of the other 4, there would be discontinuities. But there's also no like square root with a variable underneath it. There's no denominator with a variable. So the domain is all real numbers. Okay. Now that we know the domain is all real numbers, that's important. Because remember, we always consider first while others don't even consider critical values where the first derivative is undefined and pivotal values where the second derivative is undefined. Okay. Let's now go ahead and take the derivative. I'm going to use Leibniz notation. What up, Leibniz? dy dx. Now look, because it's explicitly solved for y, if this were a free response, you could go straight from y to dy dx. That indicates your method. If you want to put a d dx with a colon in front of every derivative you take, because we have to do that when it's implicit, feel free. Remember, the goal is not just to get the right answer, but to communicate. And this is, again, like a stage note. It says, hey, I'm about to take the derivative with respect to x, and here it is, d dx. All right. So the derivative of 3 is 0. The derivative of sine of x is cosine of x. All right, there's the first derivative. Now let's take the derivative again. Again, you don't have to put d dx because it's explicitly solved. Remember, the second derivative is d squared y over dx squared. And what's the derivative of cosine? Negative sine. Okay. So now I have my second derivative. I want to find the pivotal values. Look first. Is it ever undefined? No. We don't have to write that down. We just consider it. If it were undefined, we would go down and kind of do the branch, the tree, whatever. But now that we know it's never undefined, we can actually just use what's right there. You could just set it equal to 0. And that's going to get a check. You always have to show the equation you're solving, indicating your method, communicating how you're doing it. All right. Now remember, here's the full-fledged factored version of f double prime, the double prime. But if I'm going to solve this, you might multiply both sides by -1, right? You might, just to solve it. Now that's where you'd have to be careful, because remember, with the first derivative, when we had the f prime, we not only used it to find the critical values, but we used it to plug back in to find the signs. It's the same thing with the second derivative. If you get rid of that negative and accidentally plug back into this version, you're going to be OFF on every interval, right? Every interval. So it's important to identify the completely intact, fully factored version. But now, let's see. I want to know what angles in radians in one rotation on the unit circle, where's sine 0? So guess what time it is, everybody? It's unit circle time. Yeah, unit circle time. It's almost as good as peanut butter jelly time. Where is sine equal to 0? Sine is y, right? Sine y. Sine y. So on the unit circle, where's the height 0? pi, 2 pi, and 0. Good. And it's a closed interval, so we do include all three of them, right? Okay, good. So these are your PVs, pivotal values. Is every pivotal value an inflection value? So now we know there's 3 inflection values? No, they're possible, right? So now we set up a number line chart. So we got X and F double prime. Now, because this is a closed interval, this is how we're going to put our numbers on our chart. We have 0 right here. It's the left interval and a critical and a PV. This is the first year I'm using, so bear with me. I usually say possible inflection value, but it's a pivotal value. And then here's 2 pi. So we can't even test to the left and right of those 2 pivotal values. So really the only one that's important is the one in the interior. So those are my numbers. Now I come in there and notice when I did my number line chart, I put beefy brackets there so that I don't go past them. I didn't put the beef. Let me shore those up. Beefy. All right. Now we pick some test values. What's a nice angle between 0 and pi that you can evaluate the negative sign of? Pi halves, good. And something between pi and 2 pi? 3 pi halves would work. You could choose 7 pi 6, whatever. This is where the unit circle knowledge comes in. I like choosing those because those are quadrantal angles. Now, we plug it back into this version here that I highlighted. So let's do that. Sine of pi halves is 1. 1 times negative is negative. And then 3 pi halves, sine of 3 pi halves is -1 times negative is positive. So this little number line chart is going to give us all the information we need. Okay. So we already found the PIVs. That's part I right there. Now we're going to find the inflection values. Is there an inflection value, or actually I should say, does Y have an inflection value at pi? Yeah. Yes. Okay. Now I don't have to justify that it's a pivotal value because my work does that for me. But remember, critical values have to. You do, right. So it's going to look almost like we did previously. Y has an inflection value, and I'm going to put IV for short. Again, abbreviate all the way up to the day of the exam at X equals pi. There's your answer, comma, because, do we say because Y changes from concave? No. Do I say because F double prime changes from concave? Nope. I say because F double prime changes from negative to positive, not in France, but at X equals pi. Okay. So again, the word pivotal value is my invention. If enough people watch Corpy's World videos or y'all talk about it, maybe it'll catch on. I think it's important to have a word, and I can't believe after 23 years is the first year that I'm using it. So
get it on late night.
Late night?
Get it on late night.
Like, oh, that's how it'll spread?
Yeah.
Okay. So just email who does late night.
Stephen Colbert.
Oh, okay. Oh yeah, he'd be on my side.
Oh yeah.
Yeah. Okay, cool. So this is the same justification that we did for first derivatives. All right. Now look at the third part. Intervals of concavity. All right. Open intervals of concavity. So it's part 3. Woo. Okay. I know. I had to shrink mine down a little bit. Okay. Y is CC up on what open interval? You can't say negative infinity to pi. This is where the endpoints are important. 0 to pi. And if you had to justify that, I'm not going to write it. It would be because Y double prime or F double prime is negative on this interval. Now, let me talk about that. It doesn't have the name of F. Look what I'm doing in my justification. I'm saying Y, and then I'm using F double prime. If this were a free response, how do you think that would be graded? I'm also using Leibniz notation over here. They would be merciful. There's only one function we're talking about. Whether you're calling it Y or F, they would be fine. It would be okay. Okay. So just be aware of that. I probably should have said Y double prime there, or the second derivative. Y is CC up on the interval from 0 to pi, since Y double prime is negative on this interval, and CC up like a cup on the interval from pi to 2 pi. And then it would be, if you had to justify, since y double prime. Oh, yeah, I put up. Yeah. No, nope, that's me. That's all me. See, so there's so much information. And from this little number line chart, it just depends on what are they asking? What do I have to produce from this number line chart? But the number line chart gives us all the information we need. Okay. No points for having it, but it helps you get all of them. All right. Makes sense? Got it? Now we can verify that because 3 plus sine of x, that's just the graph of Sahala. And the plus 3 moves everything up 3 units. So if you wanted to sketch the graph, here's the sinusoidal axis that used to be the x-axis. It's now up at 3. And it goes all the way up to 4 and all the way down to 2. And then here is 2 pi. Here's pi. Here's pi halves, 3 pi halves. Sahala, axis, high, axis, low, axis. So concave down, concave up. Is that the same result we got? Yeah. So if they gave you this problem and it was a free response, could you draw the graph of Sahala and use that to answer the questions? They're not going to do that. I did this on purpose so that we can compare and say, oh, the analysis jibes with the graph. It works. So now we use it in earnest. Yeah. No, because I'm going to ask you for the open intervals where it's increasing and decreasing. It goes back to the same argument on whether we use open or closed brackets for intervals of increasing, decreasing. I'm an open interval kind of guy. So I'll ask for open intervals. Okay. All right. Any questions on that one? Do we have time? We have 10 minutes, right? Yeah. Okay. So what's going to happen from now on is the blue ones, those are going to be the extra enrichment type problems. I'm not going to do those in class. I would encourage you to do them, but I'm not going to do them in class. I might just record videos of them so you can watch them if you want. Okay. Now let's look at part B. Same thing. F is, we have a name now, F. Okay, got it. Frank, Fred, whatever. 6 times x squared plus 3 to the negative first. What's the domain? Well, it might be useful to write this in a different format, right? It's the same as that. Having 2 different versions of the same thing is not a bad idea. We have a denominator now with a variable in it, right? Is that dangerous? Potentially. But is x squared plus 3 ever 0? No, it's 3 at the very least. So even though there's a variable in the denominator, nothing's going to make it 0. So guess what the domain is? All real numbers. Ooh, that was a close call, right? And now we proceed. I want to get to the second derivative, but I got to go through the first. Now, which version do you want to take the derivative of? The one I gave you or the one that I wrote in red? I like the one I gave you too. So keep that in mind. Had it been the one that I gave you in red, you could use the quotient rule, but because the numerator is a single value and not a variable, you would want to bring the quantity to the top, especially because we're going to the second derivative. The chain rule is a lot faster for repetitive derivatives than the Hody-High rule. Okay, so here we go. F prime, chain rule, -6 times x squared plus 3 to the negative second times 2x. Okay. Now, this is just a way station. We're not going to stay very long. We're not going to analyze it. We need to get to the second derivative. But should we rest for a while, or sit for a spell, as they say? Get a drink of water before we move on? Yeah, let's clean it up. Let's clean it up. The -6 and the 2, we can call that -12x, and then times x squared plus 3 to the negative second. All right, now I need to take the next derivative. It's going to be a little bit more fun, ain't it? Because now I've got a variable factor, and now it's a product rule. Yes, yes? Yeah. See, that's the only bad thing about second derivative information. You need to get to the second derivative, and that can be quite a task, right? But we're up for it. Here we go. 2 factors means we have 2 terms. The derivative of the first is -12. The second goes along for the ride. Plus, the first goes along for the ride. Now, notice how I'm treating that negative in front. I'm just calling that factor -12x, and I put parentheses around it. So then I put plus, the first term goes along for the ride, And now the derivative of the second is going to be, let me put brackets here, -2 times x squared plus 3 to the -3rd times another 2x, close bracket. So again, that's just to show the grouping. F prime g plus fg prime. Two factors, two terms. All right. Now all I got to do is set it equal to 0 and solve, right? Oh my gosh, that's going to be a task, right? Yeah. Because we're going to be setting it equal, we're going to want to simplify it first. So before you set it equal to 0, just go through and house clean here. And you can factor out least powers, or you can put it in quotient form. Let's do least powers first. I'm working straight down, so the first term is just -12 x squared plus 3 to the -2nd. I'm going to leave it in the numerator. This one, what do I got? Well, I got a negative times a negative. See that? That's going to be a positive. And then I have a 12x times a 2 times a 2. So that's going to be 48x squared. Yeah, there's two 2's. So 48x times x is x squared, and then times x squared plus 3 to the -3rd. That's just a cleanup. That's combining like factors. Well, they wouldn't divide out because we're multiplying both of them, right? -2 times 2 is 4, and then 4 times 12. If there was a 1/2 somewhere, yeah, it would divide out. Now, from here, we could factor out least powers. Let's do that. What number do we have common in both? A 12? Now, if there's a negative in the front, you don't want to flip the terms around. I would recommend factoring out the negative. And then least powers. They each have some part of x squared plus 3. Which one is smaller, -2 or -3? Again, we're looking at vectors. -3 is smaller, right? It's more negative. That's why I factor out least powers. And then from here, I'll put beefy bracket. So what's left within the first term? Well, look at the numbers first. When I factor a -12 out of a -12, and again, you can imagine like there's an imaginary division sign right there. Yes? Okay. So the -12s are going to divide out, leaving a 1. And then what part of the x squared plus 3 are we going to left with? Well, again, imagine there's a division bar. When you're dividing and the bases are the same, you subtract. -2 minus -3 is really -2 plus 3, which is 1. Yeah, if you factor out enough least powers, you'll see that that one on the inside, especially when it's coming from the power rule, should end up being nice. And then I'm going to be left with the -4x squared. Okay. This is the quickest, fastest, most efficient way. I took fastest. Ugh. I took a -12 out of a 48, giving me a -4, an x squared, and then I took this whole piece, right? Now let's clean it up. Here's the last step. We're going to put it into single fraction form. I have a -12 in the top. This piece here to the -3rd, you go downstairs. Have a good time down there. And then look, it's to the first power. So really, I can drop the parentheses. There's nothing to expand or distribute, so I can combine like terms inside, can't I? So x squared minus 4x squared is -3x squared, and then plus 3. Now there's one more thing I can do. Look at the numerator, -3x squared plus 3. Can I factor anything out of there? Yeah, not just a 3, but a what? If your leading coefficient is negative, factor it out. So when I factor the -3 out of here and multiply it by the -12, that becomes positive 36. And then I get x squared minus 1. Oh, hot diggity donut. I am finally at my full-fledged factored form of f double prime. It's not fully factored. X squared minus 1 is a difference of squares. So if you want to factor that, x minus 1, x plus 1, that's fine. But all that hard work in getting to this algebraic toil, it's going to pay off now. This problem is right there at the envelope of the amount of work you're going to have to do. I have had some much more challenging problems in the past, and then like students don't return for day 2, and I'm like, I wore them to a nub algebraically, right? But it's kind of fun. Now, if you want to simplify it this way, watch, you can work off to the side. You can put that as negative 12 over x squared plus 3 squared. And then you could say it's plus 48x squared all over this, x squared plus 3 cubed. And then you can get a common denominator. If you like that better, I don't care which method you use. On here, you would just have to multiply this by x squared plus 3 over x squared plus 3. So if you like that better, go for it. It works great. I'm trying to expand your horizons. All right, so now is f double prime, we're looking for the pivotal values now. Is f double prime ever undefined? Well, it would be when the denominator is 0. Is the denominator 0? No. So at least we considered it. You don't have to write it. Is it ever 0? Yeah. So f double prime, I don't have room to set it equal to 0 up there. So I'm going to set it equal to 0. And that's going to be when the numerator is 0. If you know what the two values are that make the numerator 0, you don't have to show setting the entire numerator 0. You can if you want. But do you know what they are? This is setting the numerator equal to 0. Yeah, 1 and negative 1. So plus or minus 1. That's going to get you a check. You have to show the equation you're solving. The whole thing is going to equal to 0 when the numerator is 0. So these are your pivotal values. Yay. Now we do the number line chart. We go back and kind of reassess. What numbers go into any number line chart? Critical values and pivotal values, but of course also any discontinuities. Do we have any discontinuities? No. So we're ready for the number line chart. Here we go. X and f double prime. There's no interval to work on here. It's all real numbers. So we have negative 1, we have 1, and now we pick some test values like negative 2, 0, and 2. And we plug it in over here. Now you can streamline your plug-in process. We're looking for the sign only. The denominator is not only never 0, but guess what? It's never negative. So I don't even have to bother plugging in there. A positive outcome doesn't affect the sign. 36, I don't have to worry about. The sign of the second derivative is going to assume the sign of x squared minus 1. And if you know what that graph looks like in your head, you already have the answer. Let's go ahead and plug in our test values. Negative 2 squared is 4. 4 minus 1 is positive 3. Plug in a 0. 0 squared is 0. 0 minus 1 is negative. And you plug in a 2. 2 squared is 4. 4 minus 1 is positive. So we can just tie up all the loose ends. Are both of the pivotal values actual inflection values? Yes. And we would justify by saying f double prime changes from positive to negative. If we listed intervals of concavity, negative infinity up to negative 1, union 1 to infinity would be concave up. And then between negative 1 and 1 will be concave down. Okay. We'll actually sketch that graph to start next class because I want to show you something important about this graph and how it's related to statistics and the standard normal curve and the probability of events from happening. Thursday, January 20th, if you're interested, that's the next home wrestling match to watch Ethan awaken and fully engaged wrestle somebody. Yeah. So that's a reminder.